All right, so let's get started. So welcome back. So this is the second half session of the tutorial, Deep Learning for Objects and Scenes. So I'm Bolei Zhou. So I'm the host and also the speaker. So nobody introduced myself. So I have to introduce myself by myself. So I'm a fifth-year PhD student from MIT. So my research is on scene understanding and network interpretability. So in previous talk, Kai-Ming and Ross talk about the state-of-the-art models for visual recognition. They achieve the state-of-the-art performance on image classification and object detections. So today I will talk about deep learning for visual recognition. But this talk is not about those fancy new network architectures. But I want to take a step back. I want to analyze the common properties of those networks, analyze the network interpretabilities across different architectures. The network interpretability is important because when you apply those AI for those critical applications like medical imaging or autonomous drive, you definitely care about what's going on inside. If the network makes some mistake, why it makes a mistake? So this is a joint work with David Bao, Aditya Khusla, Agatha Oliva, and Antonio Taraba. So deep neural network have been widely used for visual recognition. People propose deeper and deeper network. From 2012, AlexNet with 5 common layers, to VGG with 16 common layers, to GoogleNet with 22 common layers, to recent residual network with more than 100 convolution layers. So people propose deeper and deeper network to achieve the best performance. But as you know, deep learning is representation learning. The final performance is just one part of the story. Here, another half of the story are the internal representations. Here are the two central questions we are interested in. What have been learned inside those different architectures? And also given those different architectures, how to compare the internal representations. To understand what's going on inside those neural networks, there are some work on network visualization. For example, the deep convolution shows those internal convolution units or filters are learning to detect different concepts. Those units at a lower layer, like layer 2, are detecting texture, surface. Those units in higher layer, like layer 5, are detecting the dog head or bicycle wheels. Backpropagation is another way to visualize the network. They backproject the learned knowledge inside the weight back into the image space. The backpropagation is further used to modify an image into another pattern. The top activated images are also used to visualize the figure-eight patterns detected by each unit. Here, each row shows the figure-eight patterns for each one of the units. The first row shows this unit detecting the pose, the second detecting dog, but it confuses some other patterns. So you can see those visualizations are qualitative. How to quantitatively analyze those internal units. Here we want going from visualization to interpretation. Giving any network weights, we can fit in a lot of testing images. Then we record the activation at each unit for each one of the layers. Then we can simply rank those images and get the top activated images. Those top activated images are further segmented by the feature map of the given unit. Here we show the top activated images for one unit. This unit seems detecting the head. Here's another unit. This unit seems detecting a lamp from the visual inspection of the top activated images. So here is the top activated images for another unit. This unit seems detecting the car, but it's confused with some bird head patterns. So here, ideally, we want to automatically give an interpretation for each one of those units. Like the interpretation for the first unit is head. The second interpretation is lamp. The interpretation for the third unit is car. Here, we also want to associate a score, a confidence score, to measure how accurate those units detect those concepts. We have some previous work to annotate the semantics of units for those different networks. Here we have we train AlexNet on places. For those of you who don't know places, places is a large-scale image database for scene classification. So the output of this network trained on places will tell you the scene category or the environment of the given image. Here we also train AlexNet on ImageNet. So here we have places camerlet and the ImageNet camerlet. Both of those networks are trained from scratch. This gives us the opportunity to analyze the internal representations of neural network. Here we send the top activated images to Amazon Mechanical Turk for crowd annotation. So basically we have 3 tasks. So we ask the worker to see those top activated image crops and give a label for each one of the units. Then we ask the worker to cross out those outlier patterns. Then we ask the worker to categorize the given labels to one of those 6 categories from those low-level concepts, colors, texture, to high-level concept like object parts, or scenes. Here is the distribution of semantic types of those 6 categories across each layers. Here, the horizontal axis shows 5 cover layers from cover 1 to cover 5. Here, the percentage of units detecting the texture keep dropping. So there are more age or texture detectors at the lower layer. Here is the object part for those units. So you can see it keep increase over the layers. There are more object part detectors in the ConvNet trained on ImageNet. Here is another plot of the object detectors discovered in those 2 networks. So you can see this image is interesting because it shows there are more object detectors emerge inside the ConvNet trained for categorize scenes rather than trained to categorize the objects. Because here, those internal object detectors are more like emergent detectors without any explicit supervision. So here is the distribution of semantic types for the scene detectors. Here, one issue is that we only analyze the AlexNet, which have only 5 cover layers, giving those different architectures how to scale up to analyze those units in all those network architectures, because there's more than 100 cover layers in residual network, and each layers have hundreds of units, so it's hard to manually annotate all of them. So here our solution is simple. So we evaluate the unit for semantic segmentation. So here is the work we published at the CVPR this year. So here we show the top activated images for 1 unit. We further segment the images using the feature map of that unit. Let's assume we have pixel-wise annotation for each one of the testing images. Then we can further use a feature map to segment the pixel-wise annotation. Then we can compute how well this unit segments those visual concepts. Here, to measure the accuracies of semantic segmentation, we use intersection over Union. So intersection over Union, just we take the area of overlap between the detected region and ground truth regions and divide it by the union of those 2 regions. So here we have the network dissection. So it is a general framework to interpret the deep visual representation. So given any network, we chop off the fully connected layer. Then we feed in a lot of images with pixel-wise annotation. So those pixel-wise annotation have concepts from low-level concept, like those color, blue, texture, to high-level concept, like dog, grass, person, car. Then we take the unit activation. Then we upsample the feature size, then segment each one of those concepts. Then we associate the most confident concept for each one of the units. To collect the pixel-wise annotation, we build up a broadly and densely annotated dataset, shorted as broadened dataset. So we pull those high-level concepts like object, scenes, parts from the ADE dataset, Pascal context dataset, and Pascal part dataset. We further pull those middle-level and low-level concepts like materials, texture, colors from the open surface and the describable texture datasets. Totally, there are more than 60,000 images with more than 1,100 concepts included in our dictionary. So after we have the network dissection and this pixel-wide annotated dataset, what we can do? So here I will show you some interesting interpretation results. We first analyze the baseline models, then we apply the network dissection on AlexNet. Here is the baseline model. So we train a baseline model AlexNet on places. So this network will tell you the scene categories of the given image. We apply the network dissection to the common file layers, which has 256 units. So here is the histogram of object detectors discovered by the network dissection. So out of the 256 units, there are totally 81 object detectors. So the most frequent detector is a water detector, then is a grass, then is a tree or skyscraper. Here we consider a unit as a concept detector when the IOU is larger than 0.04. Here we show some sample unit annotation results. So here is the unit 79 in common phi. The interpretation given by our method is car. So IOU is 0.13. So here in another unit, unit 107. So the interpretation of this unit is rope. So the IOU is 0.15. So you can see those IOU seems pretty low compared to those supervised trained object detector. But I should emphasize that those units just emergent detector inside the intermediate layers. We don't put any explicit object supervision to train those detectors. So here we show another 2 units detecting the same concept. The unit 144 and another unit 200, they're detecting the mountain concept, but they are detecting different kinds of mountain. The first one detects those grassy mountain. The second detects those snowy mountain. This maybe also explain why the IOU is low, because they detect that fine-grained concept for the concept category. So here is a dissection report generated by our method. Our method not only identifies those object detectors, it also can identify those part detectors, the scene detectors, and the texture detectors. So here are the histograms for all those different concept detectors. We can further summarize those histograms into one bar. So this bar showing the number of unique detectors in each one of the concept, from high-level concept, object parts, scene to middle-level and low-level materials, texture, color. Before we apply this network dissection to different architectures, we want to justify an issue. So is interpreting individual unit meaningful? Here is a paper 3 years ago called Intrinsic Properties of Neural Network. So I give a quote here. This is, there is no distinction between individual high-level units and the random linear combination of high-level units. It suggests that it is a space rather than the individual unit that contains the semantic information in the high layers neural network. And then they show some examples. They show those images on the left. They show those single unit activation from the visualization. It seems detecting some pattern. When you do random projection and you random combine those unit activation, you still can get those nice visualization. So we want to justify that interpreting individual unit meaningful. So here, we already show that individual units are detecting those visual concepts. They are detecting reasonably well without any object supervisions. Here we conduct experiments that we generate a new layer. So we generate this yellow layer by random combine those unit activation. Then we generate a new layer without any training. Then we apply the network dissection to this yellow layer to analyze do concepts associated with the individual units or the whole feature space. Because when you do random combination, it's a feature space represents those concepts rather than individual units. Here we apply network dissection to baseline model and also the random combination. So you can see after random combination, the interpretability of the random combined network drops a lot. Like for the object detectors, it's dropped from 40s to 10 on the AlexNet trained down places. So this experimental result shows those units is aligned with concept rather than the feature space to represent those semantic category. We also apply this to the AlexNet trained down ImageNet. So in the AlexNet trained down ImageNet, this phenomenon is not that significant. So it drops, but it drops like 50%. So that's maybe one of the reasons why previous research shows that there is no distinction between unit and feature space, because they only evaluate the model trained on ImageNet. Also, they rely on the visualization rather than the quantitative interpretation to analyze the interpretability of units. So here is our takeaway. So it is meaningful to interpret individual units. Also, individual units do have quantifiable semantics. Here, we further apply the network dissection to analyze those major architectures and see how the interpretability of the network change across different architectures. Here we have AlexNet, VGG, GoogleNet, residual network, trained on ImageNet and places. So here is a histogram of unique detectors for the AlexNet trained on ImageNet and trained on places. So you can see the texture detectors are almost the same across those two networks. But the number of unique detectors for the object categories are different. There are more object detectors in the AlexNet trained on places. So we further include the VGG GoogleNet trained on ImageNet and places. So here the vertical axis already changed. So there are much more interpretable units in those deeper architectures as GoogleNet, VGG. We further include the residual network trained on ImageNet and places. So you can see the residual network trained on places have the largest number of interpretable units. They have a lot of scene detectors. They also have the largest number of object detectors compare all those different architectures. Here we show some sample units. So here is the unit detecting the house in AlexNet, house detector in VGG, house detector in GoogleNet, and another house detector in residual network. So you can see those house detectors have different IOUs. They keep increase over when you have a deeper network. Also, the residual network can detect a more compact house compared to the AlexNet house detector that can only detect the top of the house. Here we show another concept detector. Here's an airplane detector in AlexNet, in VGG, in GoogleNet, and in residual network. So the IOU for those detectors also increase over the architectures. And you can see this airplane detector in residual network even can handle the change of scales of the airplanes. They can handle some occlusion case. So here we show another train detector in AlexNet, in VGG, in GoogleNet, in residual network for the train detection. Here you can see the residual network have a very nice train detector. But from the visualization, it seems it's worse than visualization. So visualization can create some conflict with quantitative scores, the IOU score sometimes. So this is why I say the visualization is qualitative. You may not believe in those visualization, but here we generate a number, then you will believe in those numbers. Here is a plane detector in AlexNet, in VGG, in GoogleNet, and in residual network. So here is the object detectors built from the AlexNet and the residual network trained on places. So there are 40 unique object detectors in AlexNet. So the residual network instead have double the size. So it have 84 unique detectors. So the most frequent detector is a water detector, then it's grass, trees. I cannot show here. So here we further show the object units built from ImageNet. So here it's not clearly. So the most frequent object detector in AlexNet and the residual network trained on ImageNet are the dog detector, because out of those 1,000 ImageNet categories, there are more than 150 kinds of dogs. So people spend so much effort to propose new architectures, they become a dog specialist. So here we further apply the network dissection to analyze the interpretability over the layers. So here, the horizontal axis shows the number of unique detectors across all those layers in AlexNet. So it's keep increase over the layers. And there are more low-level detectors in lower layer, like COMP1 have more color detectors compared to those layer 5, they have more object detectors. Here we further show the AlexNet trained on ImageNet. So the number of unique detectors for high-level concept also keep increase. But noticeably, you see there are more object detectors in the AlexNet trained on places compared to the AlexNet trained ImageNet. This is interesting because we don't give any object supervision to train the AlexNet on places. We only have the scene labels. Those object detectors are emergent detectors inside the layers. We further apply to the VGG and the residual network trained on places and the ImageNet. So you can see there is a general trend. As you go deeper, there are more unique detectors for those high-level concepts. Here for the residual network, we just subsample some layers. So there are some intermediate layers across those sample layers. So there are much more thin detectors as the last layers of a residual network trained on places. So our next experiment is that we analyze those network architecture trained from self-supervised learning. So the convergence from self-supervised learning. So there is a general trend that people want to train network without using millions of image annotations. So they train convergence without using the image labels. Here I list some self-supervision tasks. For example, this one, they train an AlexNet using the neighborhood relationship of those patches. So they train an AlexNet to predict the neighborhoods of those patches. Now here, this self-supervision task train the convergence to solving a puzzle. So they take a 3x3 grid and then shuffle the orders of those patches and train a network to recognize the permutation patterns of those patches. So here's another recent work on colorization. So they get a gray image and a color image, then they train a convergence to colorize the gray image into the colorful image. So here's another self-supervision task. So they train a convergence to predict the audio index given the video frames. Here, totally, we include 10 different supervision tasks. So those self-supervised network using the same architecture, the AlexNet. Here is a histogram of number of unique detectors across those 10 different self-supervision tasks. So more or less, there are texture detectors across those different supervision networks, but there are more object detectors in the audio supervision compared to those detectors from the colorization self-supervision. So here we also list the AlexNet trained on places and the ImageNet. So those networks are from supervised training. So those networks from supervised training have much more semantic detectors or interpretable detectors compared to those supervised AlexNet. Previously, people trained those self-supervised network, then they compare the generalization of those deep features. Basically, they take the network from the self-supervision and evaluate on a supervised task for some image classification task. Then they show they can match the deep features trained from supervised learning. Here we provide another viewpoint to look at those features to compare their semantics in the internal representations. Here we show some sample network from self-supervision. So here is the architecture from the self-supervision network trained to predict audios from the video frames. So you can see there are a lot of texture detectors, but still there are some object detectors. So here is the object detectors. The interpretation is a car. So here is another object detector in this network is a creek. So here are not heat detectors. So you can see those object detectors are those concepts that can generate some sounds. So those concepts can help the network solve the association of the audios and the videos. Here we further show a network trained from colorization. So they take the network and train a network to colorize the gray image into colorful image. So you can see there are much more texture detectors in this architecture. Because maybe to solve the colorization task, you can simply just memorize the association of color and textures, and you can solve the task. But there's still some object detectors. So here we show one texture detectors. So it detects those banded texture. So here's the object detector detecting the tree. Here is a object detector the hat. So here, lastly, we further analyze when and how a concept learned during the training. Because after we have this network dissection, you can analyze a lot of interesting things happening inside the convergence. Here I will show you some interesting applications. So here I will show you a video. So this video shows the emergence of interpretable units during the training process. Here the horizontal axis is the training iteration, and on the right shows the accuracy on the validation set. So here I will play the video. So you can see over the training iterations, as you have more training iterations, the number of unique detectors across those 6 concepts keep increase. It's go along with the validation accuracy. Previously, people train a network, they only monitor the validation loss, then they use the validation loss or validation accuracy as a things to determine whether the training is good or not. Here we provide an alternative way to help you debug the training process. So here let's zoom in one individual unit during the training. So here we apply network dissection to each snapshot. Now we focus on one unit. So at the beginning of this unit is detecting those colors, like some just red colors. Now I'll play the video. So you can see as the training iteration going, the concept detected by this unit keep changing. So finally it's converged as a car detector. So there's some intermediate stage that this unit first pick up the rope before it become a car detector. We further apply the network dissection to analyze the transfer learning. So this is a common scenario for deep learning application. Like you have a pre-trained model. Let's say you have a AlexNet trained on places or trained on ImageNet. Then you chop out the fully connected layer. Then you fine-tuning this network pre-trained model on another data source. So previously, people working just focus on the final performers. But here we can analyze how those internal units change from one data source to another data source. Here I will show you one unit. Here is a unit in the common file layers of AlexNet trained on ImageNet. At the beginning of the fine-tuning, this is a dog detector. So it's detecting the white fur of some dog. So then we fine-tune the network to another source, 2 places, for scene classification. So you can, let's play this again. So at beginning is a dog detector. Then gradually it's converged to a waterfall detector. So you can see before fine-tuning, so it's a dog detector. Then it's gradually mutated or evolved as dog detectors. Those 2 concepts are different, but they share some low-level similarities. Like they are more like a white and a black stripes. Here we take a look at another unit. So here is the unit 52 at common file layers. So at the beginning, this unit is just a green concept detector. So we detect those bluish, blurrish green patterns. So we fine-tuning this AlexNet trained on places, trained on ImageNet to places, and see how this unit mutate from one data source to another data source. So you can see how it change. So this unit starts from the green pattern, then it's mutated in the grass detector, then it finally converge as a baseball field detector. So you can see before fine-tuning, this unit is just a green detector. So those 2 pattern concepts are different, but they still share some low-level similarities. Like the green is more, they share some greenish similarities between the 2. So here we have another unit. So at the beginning, this is a waterfall detector. So it's detecting the waterfall pretty well. Then we fine-tuning the pre-trained model to ImageNet and see how it change. So you see during the fine-tuning, so this waterfall detector unit involved as a dog detector, because there are so many dog categories in ImageNet. So those networks need to spend their capacity to represent the parts of the dog to differentiate those different categories. So you see before the fine tuning, this is just a waterfall detector. So those two patterns share some similarities. It's like white and black stripe patterns. So here let's see another unit. This unit at the beginning of the fine tuning is a stripe detector. So this is detecting the geometric, like top of buildings. So we're fine tuning this network to image that. Let's see how it changes its patterns. So let's play this again because it's a fun example. So I really like this. So you see this detector at the beginning of fine tuning is just a stripe pattern detector. Then after we fine tuning this to ImageNet, it changed the pattern to the dog ear detector. So before fine tuning this stripe detector, you see those two concepts share some similarity, like geometric similarities. So our network dissection also can apply to other applications, like to analyze how those batch normalization drop out to affect the interpretability of neural network. So welcome to our poster session. So we have a poster session and oral session on Sunday. So here is a conclusion. So hopefully I will convince you that the deep representation can be interpreted quantitatively. So when we design those network architecture, besides thinking about the final performers, we also need to think about the interpretability of network architectures. Like we want to go in deeper to have a higher performers. We also want to visualize and interpret what's going on inside. So how to better make the network explain itself, I think it's a future goal. So this is the end of my talk. So welcome any questions.
Hey.
So a quick
question.
Quick one. Okay, you have like maybe 100 specialized detector, but how many different outputs you have in this very deep nets? So the question is, what are these other layers representing, or these other features?
So the final output of the common net is to predict ImageNet is more like they have 1,000 categories. For the places common net, there are 365 different outputs. But for the intermediate output, there's just a number of units at each layers. So you can consider it's just the number of units at in previous layers at the output. So totally, so in our dictionary, we include 11,000 or 1,100 concepts in our dictionary.
You just showed these videos of the fine-tuning and how these concepts changed. Did you ever observe that units were just stuck and refused to change during fine-tuning?
Yeah, absolutely. So there are some units just stay in there. Like when we train ImageNet to places, there are always some dog detectors stuck there. We don't have so many dog category in places, but they're still there. They are more like a local minimal stay in there. But there are some units involved from one source to another source. So how to quantify them is, I think, it's ongoing research.
Okay, but would you say that it's like a minority, or is it actually like a problem?
I think it's about 1/3 of the units keeps the same.
Okay, thank you.
Yeah, sure.
Hi, thanks for your talk. I had a question about so in a given layer, maybe there's 256 feature channels, and maybe, I think from your paper, it sounds like only a very small minority or actually any sort of detector. Can you talk about the other majority of feature channels? Like what kind of descriptors are they?
Yeah, so in our case, there are about 1/3 of units are doing those concept detection. So another 2/3 of detector, so they have some lower scores aligned with our concept in our dictionary. because there are some color detectors, they don't include it in our data set. So this is one issue. So another issue is that some of those units are doing more like distributed coding. They jointly represent some concept, so which make their IOU score lower than our threshold. So there are less unit detectors.
In a lot of your graphs, you showed unique detectors or unique representations. Have you tried normalizing that instead of just by like absolute number, by how many feature maps there are to kind of see as it grows, does it grow like with a percentage of number of feature layers?
Yeah, so that's a good question. So here, those different architecture have different unit at each layers. So here, that's why we show the number of unique detectors instead of number of detectors. Unique detector can measure the diversity of emergent detectors. So here we use we can further normalize that. So that's the end of the talk. So we will have our next speaker. So our next speaker is Professor Xiaogang Wang. Xiaogang is a professor at the Chinese University of Hong Kong. So he is a driving force behind the deep learning research at the Chinese University of Hong Kong, which makes the university at one of the top research institutes for deep learning. So let's work on Xiaogang.
Okay, thank Bolei for the introduction. Actually, Ross has given a nice tutorial on the object detection from image. And so this is the last part of this tutorial. I'm going to talk about object detection from video. Because in many application scenarios, for example, in surveillance, driving or robotics, and we do stream. Okay, so beyond the object detection from students, focus on two things: and how to this tubular. Want to explore how to make better modify this classification score to improve the detection. And so far, ImageNet object detection in video, this challenge is still kind of most well-known benchmark for object detection from video. So in this benchmark, it has 30 classes, and you can see this example from these classes. And also in each video, it includes multiple objects. And these objects could come from different classes, and we also use a MeAP to for the evaluation. And here you can see some examples of object detection from videos. Actually, quite challenging even in the same video, and you can observe the large variation on the scale, and also have the occlusions and the deformation of the objects. And so this outline of this talk, we're going to talk about the three works related to tubulate-based object detection. So in the first one, we basically select region proposal, which with a high detection confidence score as a seeding point, and start from there to do the tracking to generate the tubulates, and then we make use of spatial and context information to do the rescoring. And the second one, we try to use the class label information for the whole video as a context information, and also we try to use Optical Flow to propagate the region proposal to generate the tubulates. And the last one, we propose this network, and have the tubulate proposal network to generate the tubulates efficiently. We're also going to review some other works related to object detection from videos. And actually, we know that in the past several years, and the performance of object detection has been improved a lot every year, and especially in the still images. And if we take a look at object detection from the video, and we can observe something interesting. And here we show this detection score on this video. Actually, you can see that this detection score has a large variation over time. So it means that if you directly apply object detector trained from still image to videos, and these are still quite sensitive to the pose variation, background, and the shift and occlusions. So this is not quite robust. This is from our experience. And also, you can observe that if you change this region proposal, do some shift the region proposals, and then we can observe that this detection score also changes dramatically. So this is also not robust to the spatial variations. So these are some problems for the directly applying these object detectors. And so in this first work, we have 3 stages for this framework. And first, we apply this still image detection to get the region proposal and detection scores. And then we're going to select the region proposal with a very high confidence detection score as the seeding point and do the tracking. And then we use the spatial and the temporal context information to improve this classification. And then we can use this figure example to demonstrate the process. And we firstly obtain this region proposal from the detection still image detectors. And then we're going to select some region proposal with very high confidence score. We use these as anchors to do the tracking. And then you can observe these tubelets obtained after the tracking. However, we observe that by using this method, there's a problem. If you directly using these tubelets for the detection, you can observe that this mean AP will be quite low. There are 2 reasons. One is these region proposals are actually generated by tracking, but our detectors are trained from the region proposal from still images. So these detectors are not very suitable for this region proposal obtained from tracking. So they could deliver quite low detection score if you directly apply this detector on this tracking result. This is one. Another issue is after you do this tracking, you actually the number of region proposal has been reduced significantly. This also causes the low detection rate. And so we try to modify this framework by using the spatial max pooling. So we have this tracking result to get the region proposal, and then we look at all the region proposal got from still image detectors, which have the large overlap with the tracking result. And then we're going to take this maximum detection score from this region proposal from still image detectors. And then we use this as the detection result for detection from video. And we also try to use the temporal convolution. And you previously observed that this detection score changed dramatically. So we want to make use of the temporal context information and do some smoothing. So we use a 1D fully convolutional network to do this. And so this is the region proposal generated from the tubelets. And then we extract some features as the input of this 1D CNN. And there are 3 types of features. One is the object detection score, and the other is tracking confidence and also the tracking anchor offset. So the idea is if you you observe a region proposal which has a high tracking confidence, you probably have a higher chance for this region to have the same class label as its anchor point, as a seeding point. And we will track that more. And if this tracking, this region is far away from your seeding point, and which means that this tracking may not be reliable. And in that case, and we probably trust more on these detection scores. So we combine all these informations together and do to predict to rescore the detections. So. And now you can see these are some results on the evaluate on the ImageNet VID data set. And so this one is, the first is the high confidence tracking. You select the seeding points with high confidence score and do the tracking. And this result is not good at all. And then after we doing the spatial and temporal, spatial mask pooling and the temporal convolution, result improved significantly. And also here you can compare with this baseline. This is a still image detection, and you observe. You can see that if you this high confidence tracking, this method, and he has a much lower performance than the baseline, even baseline of the still image detection. So this is caused by the two problems I mentioned before. And here is some result from this that framework, and it's kind of okay, but still you can observe some false alarms, and some parts have false alarms and also misdetections. So we need further improvement on that, and more results. All right. So we're going to make a further improvement into one is to improve this tubeless region proposal, and the other is to make a better use of the context information. So so we have two branches. You can see this the green one, the upper branch. So this is the method we just talked about, and the lower branch. This is something new. We add to these frameworks. So these two branches, they will generate some different tubeless, and also for tubeless, they have the different classification score. So finally, we have another model to do the combination to do the ensembling. Let's see how we make use of the multi-context suppression. So if we do detection at every frame, and all these region proposals, they have the detection classification scores, and then we will going to sort all these detection scores of all these proposals in the video in a descending order, and then we're going to the classes with high ranking we donate as the confidence classes, and also we have some classes, the scores of the classes with low ranking, we further suppress them to reduce the further alarm. So basically, make use of the class information from the whole video, and we guess which classes are dominant in this video. We're going to give them further improve their score, and for those others, they may be a false alarm. We suppress their scores. And also we can try to use the optical flow and to improve this tubeless generation. So for each frame, when you detect the region proposals, you may miss some objects, and on each frame. But if we can compute the optical flow, and we can propagate these region proposals to adjacent frames and to reduce the misdetections. And the propagation result in redundant boxes, but at least can be handled in the later stage by using MS. And now we can see that so this framework, and we generate two types of tubelets, and each tubelet also could have different scores. So finally, we have the model average model combination stage. So we need to combine different types of tubelets together, and also do the averaging on the for each tubelet. It has multiple classification scores. We do the averaging and finally do the NMAPs. And so this is the component analysis, and to show the effectiveness. And we can see this the craft and the DeepITNet. These are the two baseline image still image detectors, and we can show their performance. They are the blue bars, and these just apply these still image detectors on the videos. And this one shows if we try to include these two types of components to make use of temporal information, and you can see that the performance can improve dramatically. And last, the red one, this is the combination of all these different detectors and different models to the model ensemble. And on the ImageNet, the challenge is to have the provided data, and another track is additional data, and these are the results on these two tracks, and you can also observe a similar trend. And these are the summaries of the quantitative results, the craft and the DeepITNet. These are the still image detectors, and these are the results. And we adding the temporal information, context information, and the tubelet generation. We got this, and finally do the model combination. And now you can see these are the so final result generate this from this framework. Right? So this quite stable, and a lot of false alarm get reduced. You can see more results. Okay, so lastly, we're going to talk about the tubelet proposal network. So in the previous two works, we have two ways to generate these tubelets. One is based on the high confidence tracking, and this is going to generate very long and sparse tubelets, but it were quite time consuming. We cannot generate because the computation cost, we cannot get too many tubelets. And the other one is we using the optical flow to do the propagation, and we get many short and dense tubelets. So we want to improve this. We hope that we can get some long and dense tubelets and quite efficiently. And we also want to keep these tubelets with a high diversity, and to incorporate long-term temporal information, and to capture global sequence features. So this is the goal of this. Here, here I show you some tubelet region proposal generated, and these are the region proposal generated from the still image detectors. And you can see that they have a large diversity among these region proposals. But there's no temporal correspondence because we didn't do any tracking on that. For in the middle column, this one, so these are the tupelets generated by regression. Right? So every frame, given region proposal, we do regression to predict the next locations. But we observe one problem for this method is that initially this region proposal have quite diversified, but after a few iterations of regression, and they will converge to objects and or to some parts of the objects. So the diversity can be will reduce significantly. So this is not very good for the detection. So we can treat this region proposal as different body parts and of the objects, and if you have the multiple region proposals, so they eventually then combine together, so they detect different body parts, and they can make this detection robust. And so we propose a network. We hope that our region proposals and can have this temporal correspondence, and also could this keep this diversity. So this is the region proposal generated by our network. Okay. So this is the framework. So we have two parts. The first part is a tubelet proposal network. Give the video sequence, and we input as the features of the region proposal, and then the output, the prediction is the motion of these region proposals. And then we get these tubelets, and then after that, for each tubelet, we can extract the feature at every frame, and we input as the input of LSTM, and then output predict the class labels. And here are some details. And actually, the naive way is you have give you two frames, and you can predict the motion of one region proposal. So, but we want to do more. So we let's say we consider a few more frames. Let's say 5 or 6 frames together. So at the initial stage, we get the region proposals. We keep their position fixed, and then we extract the features at all these locations. And then we use this as the input of the network, and then we try to predict the motion of these region proposals, and to get predict to get the tracklet. And then we got the new positions of the region proposal, and we repeat this process, and to keep doing this tracking. And then we can, in this way, we can track quite a long, get quite a long tracklets. And so we actually predict the motion of the ground truth object instead of the moving the region proposal towards the object, so in order to increase the diversity of the tubelets. And we also keep we have multiple region proposal. We try to keep their relative locations, and for temporal windows. And we try to make use of temporal information, and to generate smooth trajectories. And after you got these region proposals, which for tubelets, we extract the tubelet features, and using input as the encoder LSTM to summarize all this information, and then decoder as LSTM to do the prediction of the class labels. And let's see some results here. And here you can see some results of the region proposals or tubelets proposals we generated. And you can see they are still can keep, during the tracking, they are still can keep their relative positions. They will not converge to the same objects. And these are the final results of the object detections. Oh. Okay, so in the last few minutes, I just mentioned a few other works related to object detection from video. So in this work is also using the optical flow. So it's quite related to our previous work. Say we propagate these bounding box or region proposals between adjacent frame. But in this work, they try to propagate the features. And then you can see if you have multiple frames, in certain frames, because of some blurring effect or the occlusions, the features may not be very good, right? So, but if you are able to capture, compute the optical flow, and you can borrow the adjacent features from the adjacent frames to improve, to ensemble them to improve the quality of the features. So that's basically this idea of this work. And you get optical flow and propagate the features between frames, and then you have the algorithm to ensemble these features. And then the results, you can see in some certain frames without in the baseline, and some objects could be missed when they have the blurring and the occlusions. But with the help of the adjacent frames, they can be detected. And another work is by using the object detection result from the previous frame as the prior. So basically, when you detect the objects as the frame T, and so this can serve as a prior knowledge. So at the next frame, and you hope that more region proposals can be generated at the location of this object you already detected. And these are some examples. Without using this, your region proposal could be anywhere. But if you already detect one object in the current frame, in the next frame, you hope that you modify these the scores of the region proposals. You want to find generate more region proposal surrounding your the object already detected. And people also could do the association among these region proposals. And you have region proposal, you match the region proposal based on the appearance, the features, and to generate the tracklet, and then rescore the tracklet, and then do MMS to use this tracklet to remove other region proposals. Okay. So in conclusion, so we here we can see that the temporal information, we try to use the temporal information for the object proposal, and also use the temporal information to modify this classification score. But there are still many challenges unsolved to be explored in the future. And we know that video-based detection, you occupy a lot of memories. And so how to manage memory usage in the GPU, and this is a challenge. And also, so far, we model this relationship between the bounding box or the region proposals, but it's the lack of modeling the relationship between different tracklets. This is another way for the first explore. And also, we currently we still don't consider too much about the speed and the computation efficiency issue for the video analysis. So they mainly try to improve the speed, the accuracy, but in real applications, speed is definitely a key issue to be solved. All right, so I'm ready to take questions. Thank you.
Any questions? So I have a question. Oh.
So it's a very general question. So there has been quite a lot of work on very efficient tracking in computer vision, which doesn't necessarily use deep nets.
Right.
And very sophisticated and low computational complexity. So why don't we try to sort of efficiently integrate it? Because optical flow is a very basic or primitive way of tracking.
So So we have to consider the computation issue. So these trackers are good. They mostly are for single object trackers. And but in the detection we have the hundreds of region proposal in a single frame. And we need you want to track all these frames. And this computation just cannot be afforded. We try this, but it just cannot on this such large scale.
Okay, so that's the end of this tutorial. So I hope you guys enjoy those talks.